Sure.
Always a nice way to start out a Saturday morning. Actually, for me it is. I love doing calculus. It's just so challenging. So last time we left off with 25.
I believe so, yes.
Yeah, and this was kind of an interesting one. It gave me a little bit of confusion when I was going through it with you, and that's because I didn't recognize something immediately. In other words, if we're going to let u equal e to the 3x, in other words, once we've made that decision, then we are looking at the derivative of the u in the numerator. So,
Mr. Cohen?
What's that?
I can't see your screen.
Let me close out some things here and see if that helps. Let's see what's going on. Can you see the integral of e to the 3x that I've written?
No.
Really? How about now?
As in, like, nothing popped up in order for me to see your desktop.
Frozen?
No, just nothing popped up to allow me to see it like it normally does.
Oh, hold on. Gosh. I'm so sorry. There's a button that I always push, says show my screen when I first log on with somebody, and for some reason I forgot to push it today.
Okay, so well, I can see now.
You can see it now. Okay, good.
Yes.
Sorry about that. Thank you for saying something. Gosh, that would have been terrible. Back to this problem. I could see that we were going to end up with something that looked like this. Okay? And I know what the integral of that is. I know what the antiderivative of that is. It's inverse tan. But what kind of threw me was this numerator. In other words, if I end up with u over that, I'm not sure I know how to integrate that. But here's the key. Remember what we're always looking for when we're using this u substitution, which is the derivative of u needs to be in the numerator because it'll end up in the denominator and we need to be able to cancel it out. Well, the derivative of e to the 3x is 3 times e to the 3x. So it will accomplish what we want it to do. In other words, it'll get rid of that u once we convert it to u substitution. And so really what we can almost look at is using, well, not really the power rule, but that's why it's hard to see. It's a little confusing. It's rare that the derivative of your u is going to be the same thing or close to the same thing. Remember, it doesn't have to be exactly the same thing. If it's off by just a constant, we can handle that. All right, let's go to some of these. Only if you've covered these. Have you covered volumes of solids of revolution?
Yes.
Okay, cool. Sounds like you covered the AB Calc program pretty good. We haven't really come across too many things that you did not cover in your IB program.
That's good.
Yeah, so far I'm impressed. I didn't realize that. Actually, I haven't worked with that many IB programs. Okay, there's our two graphs. There's x squared, and here's y equal 3x. I haven't drawn it quite properly. I didn't put the proper slope on the y equal 3x, but close enough. Okay, so when we revolve this section around the x-axis, we are going to end up with a shape that looks a little like this, and it will be a solid. And if you're looking at it from this direction, it's going to look like an open flower.
Okay.
Can you picture it?
Yes.
Okay. So how are we going to figure out the volume of that flower? Remember that when we do volumes of solids of revolution, we use usually what shapes to chop it up into?
Rectangles.
No, we use washers, or we use discs. And,
okay, sorry, I don't remember the formula exactly.
Okay, that's okay. We'll go over it here. There's three kinds of objects you can use. You can use discs, like a coin. You can use washers, just like what you would imagine, a hole in a coin. Or you can use cylindrical shells. Now, you may not have covered cylindrical shells. I don't know. Did you?
No.
Okay. Cylindrical shells are by far the toughest to figure out. A cylindrical shell would be if you took a dollar bill out and turned it into a cylinder.
Okay.
That's a cylindrical shell.
Okay.
In other words, you can make up solid objects by just putting a bunch of cylindrical shells together, all of different radiuses and different heights.
Okay.
Just like you can washers and discs. Well, what would we use to make up this object? Washers,
probably
discs, or the third one, cylindrical shells, you haven't gotten. And there are no questions about cylindrical shells on this AP exam either. So.
Okay, so then probably washers.
Yeah, in other words, we need something with a hole in it, because this whole area here is going to be a hole. I can put one cylindrical shell right there that has a tiny hole, and I can put another one right there that has a bigger one, and a third one right there, and a whole series of them, each one of them having a different size hole in the washer, and I could put together a object. If you gave me a box of washers of varying outside and inside radiuses, I could put them together in a way that looked exactly like this flower. Okay? And then what I'm going to do is add up the volume of all the washers. Well, what's the volume of a washer going to be? It's going to be the area of the washer times the thickness.
Minus the, right.
And the thickness, you can see that's dx, because that's the axis of integration. So we are going to integrate along the x-axis, and because the skinny side of these washers is perpendicular to the x-axis. And so what's the area of this washer? If this outside radius is, say, capital R, and the inside radius is little r, what's the area of that washer?
Would it be like pi capital R squared minus pi little r squared?
Yeah, and I can factor the pi out, so you end up with this. And that's the formula for washers. So I'm going to integrate, and I'm going to take the pi outside. That's just kind of standard operating procedure. Capital R squared minus little r squared dx. Which one is the capital R squared? Or which one's capital R? Which function? It's the one that's above. In In other words, the y equals 3x is always the big R. Notice that by the time my flower gets out to here, my outside radius is this.
Okay.
So your outside radius is always the function that's on top. And your inside radius is clearly the y equal x squared part.
Okay.
Okay? What are my limits of integration going to be? This point here, obviously,
right,
to this point here. What's that point on the x-axis? It's where my two graphs intersect.
Right.
Okay, so where does x squared and 3x intersect? Where are they equal to one another? If I solve x squared equal 3x.
Wouldn't they equal each other when x equals 3?
And 0. There's 2 points.
0.
So this point is the 0 point where they intersect, and this point is 3. So I'm going to do my integration from 0 to 3. And it's going to look like this. The integral from 0 to 3, and big R is 3x, so it's the quantity 3x squared minus x squared squared, because that's the second function. That's little r, is x squared.
Right.
And then the whole thing is dx.
dx.
And now you can see that the problem becomes pretty easy. In other words, that's an easy integral to do. The integral, let's just give you a little practice. See if you need it.
Probably.
Probably you don't, actually. So how do I solve that? Leave the pi. Leave the pi.
Yeah, leave the pi out, and then with the large bracket thing, with 0 to 3.
First of all, we have to integrate each of these polynomials.
Right.
In other words, you have to find the antiderivative of it. Our first step is to get rid of the integral sign.
So that would be 3x cubed.
For that part.
Minus 1/5 x to the 5th. Plus c. Wait, no, not plus c, because it's a definite interval.
No plus c. And I don't know whether... Is that a bracket that they... It is a bracket, isn't it?
Yeah.
All right. Well, that's all that means is we shouldn't use brackets here. We should use parentheses, so as to not confuse the issue. That's relatively straightforward, because we can see that when we substitute the second one, it's going to all be zeros. So the answer is going to be whatever that is when we substitute x equal 3.
Right.
So that's going to be pi times 3 times 27 is 81. What's 3 to the 5th? 3 times 81, 243 over 5. So, looks like it's going to be A, 162 pi over 5. In other words, if I do this operation, I have 405 fifths minus 243 fifths. That sounds like 162 fifths. All right. And of course, where you use washers, where you use discs in place of washers is when you don't have you're not going to have a hole in there. Not everything's going to give you a hole in it. In other words, if I were to merely rotate that function about the x-axis, I end up with a solid-looking object that has no hole in it. So if I was solving this problem, I would use disks.
Right.
I guess you can always kind of, it would actually probably be, I don't know if it's easier or harder, but you can always use washers and the inside radius can just always be 0. And that would be the equivalent of using disks. You see what I'm saying?
Yes.
Okay. And now, when you use cylindrical shells, I'll just say this much about it because you'll definitely be getting cylindrical shells in your calc class. The main difference between using cylindrical shells and disks is the axis of orientation. Notice this object here. After I've revolved this line around the x-axis, I have a three-dimensional solid here. I can use disks, and disks are always going to be perpendicular to my axis of integration. But I could make up this object also with cylindrical shells. The only difference is the cylindrical shells would be parallel to my axis of integration. And that's when you use, so in other words, most every object that you can make up with a bunch of disks, can also be made up with a bunch of cylindrical shells. And what causes you to choose one over the other is usually the axis of orientation. We won't get into that today, but they'll give you examples. Like these kind of objects can be formed by either one. The difference is in one case you would integrate along the x-axis, and in the other case you would integrate along the y-axis. And that's certainly always very doable. There's no preference given to the x-axis. Sometimes things are better done integrating along the y-axis. For example, if I give you two curves like this, and I say, what's the area between those two curves? It's going to be difficult to break that thing up into a bunch of rectangles, right? Vertical rectangles?
Yes.
But notice how easy it would be to break it up into horizontal rectangles. Which means the skinny part of my rectangle is in this direction, which means I'm going to have to integrate this thing along the y-axis, which means each of these has to be defined as a function of y, not a function of x. These might come to you as functions of x, but you can turn it around. You know, if I tell you that y equals x squared, I can solve that for x. X equals plus or minus the square root of y. Now I have a function of y. So when you are integrating along the y-axis, the most important thing is to know that your function has to be a function of y. You cannot have a function of y and integrate it along the x-axis, or a function of u, or a function of r. In other words, to integrate along the x-axis, you need a function of x. All right. Slope fields. Did you get to slope fields at all?
A bit.
Let me explain just a bit. I'm not going to go into them heavily. They can be kind of confusing. They were pretty confusing to me when I first saw them, and it's only because I didn't have somebody recently that could explain them to me. But they're not that hard. If I tell you that dy dx is equal to 2x Now, remember how to solve that differential equation? Separate the variables and then integrate both sides.
Okay, wait.
In other words, you want all the variables in x. Anything with x in it, you want on the right side. Anything with y in it, you want on the left.
Okay.
So the first step is pretty simple. dy equals 2x dx. Okay? Now, my object is to solve for y. Whenever I have a differential equation like this, my goal is to solve for y. Well, to solve for y, I have to integrate the left, which means I have to integrate the right. And now I have y. The integral of 1 dy is just y. And that's equal to x squared plus c. Okay? If I wanted to represent that graphically, I would end up with a slope field. Notice that there are a bunch of, depending on what c is, these are my solutions. See why each of those is a solution? Because as all c is a vertical shift. So I'm going to take whatever parabola I would get from y equal x squared and vertically shift it by some constant. And c can be anything. So I basically have an infinite number of these slopes or graphs, which I can now turn into what's called a slope field, where I don't actually draw the entire curve, I just draw pieces of it that approximate the slope. And I would end up with something that would be covered in these small dashes, where each dash indicates the slope. And in this one, it's relatively simple. It's just going to look like that. Okay, so if this was the question, we would look for the slope fields that appear to be a series of parabolas. In other words, A kind of looks like that.
Okay.
But, hold on, that's not the function of A, so that's not the answer. But if, no, A doesn't look like parabolas. In other words, notice over this part of A, it's beginning to look more like a sine curve. And in fact, this looks like it might be y equals sine x plus c. Okay? So what do we have here? This is fairly tricky, but it's not really tricky. It's just interesting. If we have dy dx equals x over y, well, now when we separate variables, we have y dy equals x dx. And now when we integrate both sides, we have y squared over 2 equals x squared over 2 plus c. And now, instead of solving that for y, see if you can spot what that is. Any clue? It's a little, you have to almost be used to looking at it in a certain way. Is that a circle? Is that an ellipse? Is that a hyperbola? Is that anything that we can recognize? Is it a parabola?
A circle?
Well,
perhaps?
if I move the x squared over 2 to the left side, I get this. And then if I want 1 on the right side, I'll divide everything by c.
So it's an ellipse?
What is that? That's a hyperbola.
Right.
In other words, whenever you have subtraction going on, between the y's and the x's, that's a hyperbola. If it was an ellipse, it would be a plus sign. And
same with a circle.
If it was a plus sign and they had the same coefficient, like these appear to have, then that's a circle. Okay? So, this is definitely a hyperbola. So now we need to look at our slope fields to figure out what looks like a hyperbola. And in fact, it's a vertical hyperbola because you have x squared being subtracted from y squared. So what we're really kind of looking for in the slope field is something that's going to look like this. And that is D.
Okay.
Okay? But that's the concept of slope fields. Because when you take an integral, you have an infinite number of solutions, because of that plus c, the slope field is merely graphing all of those possible solutions. Now, you might think, well, why have this complicated slope field if it's all the curves are just going to look the same vertically? Well, they don't. Sometimes when you solve a differential equation, this c turns into a multiplier, not an adding. So it's not always the different solutions are just going to be vertically shifted from one another. It's very rare, in fact. So the slope fields can look different for different differential equations. Now, before we leave slope fields, let's talk just a little bit about this. There's another way to do this problem.
Okay.
What this is saying is that this is the slope anywhere you are. In other words, if, say I go to the point 4, 4, where x is 4 and y is 4.
Okay.
I need to find a slope of 1, because this tells me that whenever x is equal to y, my slope at that point has to be x over y. That's what differentials mean. In other words, this is telling you that the slope anywhere on your slope field, if I go down to D and I find the point 3, 3, I better have a slope of 1. If I find the point 4, 4, I better have a slope of 1. If I go to the point minus 4 plus 4, now my slope better be minus 1. And it is. If we were to do, in other words, if we do not solve this differential equation, and this is really the essence of slope fields, is that you don't have to be able to solve. Differential equations can be bears to solve. I mean, they're just like integrals. And I mean that differently. In other words, integrals are bears to solve. There's about 18 different methods. Same thing with differential equations. You can't always separate the variables. And when you get differential equations where you can't separate the variables, then you have to use all these exotic techniques. I mean, it's a full semester's length course, differential equations. And so you don't always need to be able to solve them. Sometimes you can take the differential equation and figure out what the slope field is because this is telling it to you. I can tell that whenever x is the same as y, my slope's got to be 1. When x is 2 and y is 4, my slope better be 1/2 on my slope field. All right, let's go beyond slope fields. I think I need to, I need to go to the next page. Oops. Number 28. I hope you're sticking an easy one in there, but what's the first thing you do to evaluate a limit?
See if you can factor it?
Well, the first thing really to do is to just substitute, right? Substitute 5 for x. But all of the challenging problems come when you get 0 over 0 after substituting. And we have to do more stuff. When you end up substituting and you get 0 over 0, you're not done. You got to go further. If you get, say, 1 over 0, well, that's infinity. If you get 0 over 1 or any other number, that's 0. So the only thing that presents challenges with limit problems is when you get 0 over 0. So we almost know before looking at this, especially when I plug in 5 in the denominator, I know that's 0. I know that's going to be 0 without even looking at it, and it is. Now it's a factoring problem. Factor the top.
X plus 7, the quantity of x plus 7 times x minus 5.
And the bottom?
The quantity of x plus 5 times the quantity of x minus 5.
Now we can cancel that with that, and now substitute. What do you get?
12 over 10.
Or 6/5. And that's the way most limit problems go, is that you can factor them into a state where it's no longer 0 over 0. Next page. Now this is the section of the AP exam where you can use a calculator if you want.
Okay.
The problems tend to be relatively not that much different, but it basically allows you to graph things and see how much you can tell from graphing them that you couldn't do on the earlier sections. 29 is the same problem as we just did. Almost identical, in fact. Instead of, it was 35 and 2t, but it's the same solution. You factor the top, factor the bottom, cancel, reevaluate. I think we can skip that one. What is the average rate of change? How can I set it up? As production goes from 300 units, in other words, as X goes from 300 units to 310 units, how do I get my average rate of change? Average rate of change is not a calculus concept. It is a pre-calc. It's an algebra concept.
Okay.
Calculus is instantaneous rate of change. So average rate of change is just the rise over the run. Okay, in other words, if I were to graph this thing, looks like some sort of a parabola, where, I don't know, maybe it does something like that. And as we go from 300 units on the x-axis to 310 units, well, the average rate of change is that rise divided by this run. Well, the key to this problem is stating it. In other words, what we want is the rise is C of 310 minus C of 300. Make sure you understand that. That's critical in calculus, is representing the y value this way.
Right.
All over 310 minus 300. That's the run. Okay. And the way we're going to come up with C of 310 is we're just going to plug in 310. So C of 310 would be 2,000 plus 8.6 times 310 plus 0.5 times 310 squared. And that's this part. And I have to subtract off that part. So I'm going to subtract 2,000 plus 8.6 times 300 plus 0.5 times 300 squared. And I'm going to divide. Notice I put parentheses around it.
Okay.
Because if I don't, I'm going to lose my signs. And I'm going to divide all of that by 10. And that's going to be my answer. And this is where another place where this problem would have to be on the calculator portion. Because otherwise we're going to have difficulty evaluating these numbers without our calculator. All right. Not concerned with coming up with the specific answer. And you'll notice that was not a calculus problem at all. That was a problem you could have given to an Algebra 1 student even.
Mm-hmm.
Okay, they want you to find the inflection points of this function.
Okay.
So let's ignore their hint for a second. How are we going to find inflection points? What do we use to get an inflection point?
The derivative?
Second derivative.
Second derivative.
Yeah, when the first derivative is equal to 0, we have critical points. And usually we have mins or maxes. In other words, if we're looking at this function, your first derivative is going to be 0 there and 0 there. And so first derivative zeros tell you mins and maxes on the function. But if I want to find out where that point is, in other words, where it changes from being concave down to concave up, that's the inflection point. That's where the second derivative is equal to 0. Okay? Now, to be honest, I do not remember covering this in Calc 1, 2, or 3. I understand the answer, but we'll go through it again. First of all, more important for you is minimums and maximums and first derivatives being 0.
Right.
In other words, if I have that function and I take the first derivative of it, I'm going to be able to tell where that occurs and where that occurs, because my first derivative is going to be 0. Unfortunately, if I have this function, which is y equal x cubed, a cubic function, and I take the first derivative of it and find out where it's equal to 0, it's right there, or right there. And that is neither a min or a max. So it's not always the case that the first derivative being equal to 0 is equal to a min or a max. And you have to apply one of two rules. The one I want to talk about is the first derivative test. And what the first derivative test says is that our 0 point, for it to be a min or a max, the slopes have to change sign on either side of it. Well, notice on this one, it goes plus, 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 comes out plus plus plus. The derivative did not change sign. The slopes are plus before that point and after that point. That means it's not a maximum or a minimum, is what it means. In other words, it flunked my first derivative test, as opposed to this one, where notice that's a local maximum because the slopes go plus, 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 minus, minus, minus. And then down here, they're minus, 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 plus, plus, plus. So in this case and this case, not only is my first derivative 0, but I pass the first derivative test, which are the slopes changing sign on either side of this point. And this one flunks the first derivative test, so that is not a minimum or a maximum. Okay? So that's first derivative, and that's the most common thing you learn in calculus. Well, there's a similar thing for the inflection points. In other words, if I want to find the inflection point right there, I take the second derivative of this function, set it equal to 0, and that is a possible inflection point. But just like minimums and maximums, not all second derivatives that are equal to 0 are inflection points. And it has what is called the second derivative test, where the sign of the second derivative has to change left and right of your possible inflection point. In other words, we're still going to take this sixth degree function. We're going to take the second derivative of it. We're going to then factor it based on this hint they gave us, because obviously after we take the second derivative, our largest power is going to be x to the fourth. You always lose 1 degree with each derivative.
Okay. And
you're going to factor out a 30 also. All of these numbers are going to be divisible by 30 after you take the second derivative of it. And so you end up with 30 times x squared minus 4 times x squared plus 2x plus 1, and setting all of that equal to 0. In other words, this is your second derivative. I don't think we need to go through it. It's a simple polynomial to differentiate. I'm sure you can do that. The hard part was the part they gave us the hint on. In other words, they told us how to factor this quartic, which we wouldn't have been able to figure out on our own. That's hard to do. That is really complex math, factoring quartics.
Right.
But, so they give us this hint, so we know that this is our answer. And of course, where is this equal to 0? It's when x is plus or minus 2, or when x is minus 1. So we have 3 possible inflection points. And if you go through each one and check to the left and the right, both of these pass the second derivative test. This one fails it. So these are our only 2 inflection points.
Okay.
Okay? They want first derivative evaluated at pi over 4. So our first job is to figure out the first derivative. What is a prime of x? Which rule do we need to use? Differentiation rule.
Chain rule?
Huh? What's your inside?
Sin x.
Okay, so let's take the derivative of the outside, multiply it by the derivative of the inside. What's the derivative of the outside?
Wait, negative cosine?
No?
No, wait, cosine.
The derivative of cosine is negative sine, but the derivative of sine is positive cosine.
Right. I always mix those two up.
What's the rest of it? In other words, the first step on taking the derivative of the outside is to just take the derivative of the outside, and the inside is still that. Now we have to multiply this whole thing times the derivative of the inside,
which is cosine x.
So now that's what we have. We have a prime of x. It looks a little strange. We're not used to seeing this, but it's not cosine squared. It's cosine of sine of x times cosine of x. Well, if I'm going to evaluate that at pi over 4, I merely need to substitute pi over 4 wherever I see x. And use my calculator to come up with an answer. Now, not quite. Actually, your calculator may have difficulty with that. Might not, but it might have difficulty with it. Shouldn't, but clearly we're going to do this from the inside out.
Right.
The sine of pi over 4 is root 2 over 2, so now we're going to take the cosine of root 2 over 2 times the cosine of pi over 4, which is also root 2 over 2. So now we're going to figure out the cosine of that. Remember, in calculus, everything is in radians, not degrees. And in fact, it has to be in radians for the derivative of sine to be cosine. When you're in degrees, the derivative of sine is not cosine. So all of calculus has to have angles in radians, not degrees.
Okay.
In other words, this will give us a number if we put it into our calculator, as long as we're in radian mode. This is just a radian, some number of radians. Again, shouldn't waste our time on coming up with the exact answer. It's not what we're trying to do here. So if f of x is equal to sine x cosine x, what is f prime of x equal to? What rule are we going to use here?
The product rule.
Okay, so what do we have?
Sine of x times sine of x plus
negative.
Right. Negative sine of x. Plus cosine x times cosine x.
So all of this becomes cosine squared x minus sine squared x. That's f prime of x. And what does it mean, critical points?
In
other words, when it says find all the critical points, the first thing I forgot to mention is obviously the first step is to take the first derivative, and it's where your first derivative is equal to 0 or undefined. That's what critical points are. So this is defined everywhere. So the only critical point is going to be when that is true. And now solving that, not terribly tough. How would you solve that?
Would cosine squared of x and sine squared of x have to equal each other in order for it to equal 0?
Yes. So that's one way. In other words, I can move sine squared x over to the other side, take the square root of both sides. their approach was a little bit different. It was treating this as the difference of perfect squares. So it's cosine x minus sine x times cosine x plus sine x, which gives you the same result. In other words, that has to equal 0 or that has to equal 0. So I end up with cosine of x either equals the sine of x or cosine of x equals the minus sine of x.
Right.
Well, what's the most common place where cosine x equals sine x? What angle? 45 degrees.
Right.
In other words, square root of 2 over 2 for both. So we know that pi over 4 is one answer.
Right.
Well, it's every 45 degree angle reference angle in the unit circle where this is true. In other words, in the second quadrant at 135 degrees. My cosine x is square root of 2 over 2, or negative square root of 2 over 2, minus sine x is negative square root of 2 over 2. So it's basically all four quadrants that have the 45 degree angle, which is answer B. This one's in the second quadrant, this is the third quadrant, and that's the fourth quadrant one. So it's every quadrant where this can be true with that. Okay, now before we leave this problem, there are some other interesting, perhaps easier ways to do this. One of them would be to recognize that that is also the cosine of 2x by a trig identity. And now this yields the same solution, but a little bit easier. In other words, it's wherever the cosine of 2x is equal to 0. And you'll notice that it's at those same 4 points. This first point would give you the cosine of pi over 2, that's 0. The next point would give you the cosine of 3 pi over 2, that's 0. So forth and so on. You're going to get zeros at all four of these points. And that's perhaps a little bit easier. I don't know. The way the book actually suggested was going back to the original, and rather than having to differentiate this and use the product rule, well, that identity is 1/2 the sine of 2x. Remember, the sine of 2x is 2 sine x cosine x? Well, sine x cosine x is 1/2. So if that's f of x, this is much easier to differentiate than this. I got to use the product rule for this. I got to use the chain rule for this, but only the 2. In other words, the derivative of the outside is 1/2 cosine of 2x. The derivative of the inside is 2. So now there's my derivative. Cosine of 2x. Probably easier to get to it using this identity than it was to have to use the product rule. And then once again, you've got 0 equal cosine 2x. So a number of ways to do that. Most important thing is understanding what critical points mean. It means where your first derivative is either 0 or undefined.
Okay.
Here if they said, what's the slope of the tangent line, what would we do? They're asking the slope of the normal.
Which is perpendicular to the tangent?
So, right. It's perpendicular to the tangent, and it's got the negative slope on it.
Right.
Negative reciprocal, the normal line. So the first step is to find the slope of the tangent line. How do we do that?
Well, the point is at 2, 1, so
We're going to evaluate it at that point.
Right.
Which means there's a suggestion there. The fact that they didn't ask us to evaluate it at just x, some x point, they're asking us to evaluate it at an x and a y, that would suggest our first derivative is going to have both x and y in the answer. Which suggests
makes sense.
Which technique to integrate it. Implicit differentiation.
Oh.
In other words, for us to come up with dy dx, I can't solve this thing for y. Try to solve that for y. You could probably spend half a day trying to solve that for y. Not easy. So it's not an easy thing to explicitly differentiate. And there's all kinds of functions like this. So implicit differentiation is probably used more frequently than explicit, just because there's lots of functions that can't be defined in y. So let's implicitly differentiate this. How do we do it?
Okay.
In other words, this is what we're going to do. We're going to take the derivative of that with respect to x, and we're going to take the derivative of that with respect to x. So when you take the derivative of something with respect to x, you basically just explicitly differentiate everything that's x, and when you run into a variable that isn't x, then you have to follow it with dy dx.
Right.
Okay, so let's start from the left. What's this? In other words, explicitly differentiate this.
Okay.
Okay, what's next?
Product rule.
Okay.
With respect to x.
We're going to have to use the product rule here. So let's do it. Here, let me put big parentheses around it.
And product rule is 1d2 plus 2d1.
Okay.
So x and the derivative of y squared with respect to x would be 2y times y prime.
There you go.
And then plus y squared, because x,
exactly.
Right.
And then the right side? Because if I'm going to differentiate the left side, I got to differentiate the right side also.
10y prime?
Huh? Now, we have to solve this for y prime. How do we do that? First of all, I can remove these parentheses because it's a plus sign in front of it.
Mm-hmm.
This is tricky, but it's something you definitely want to know how to do.
Okay.
Gather every term that has y prime in it on one side of the equation. And put everything else on the other side. With me?
Yes.
Okay. And now factor out the y prime. So if I factor out the y prime, I am left with that. Okay. And now divide both sides by this, what's in parentheses. So you end up with y prime equals minus y squared minus 3x squared, all divided by 2xy minus 10. Now I've solved for y prime, and evaluating it at that point I can do, because I'm just going to plug in 2 wherever I see x and 1 wherever I see y. And that will be the slope of the tangent line at the point 2, 1.
Right.
Then you take the negative reciprocal of that to find the slope of the normal line. Okay? And that's the way most implicit differentiation plays out, is you end up with multiple y primes and after you've taken the derivative, and then you have to gather them all together, factor them out, so forth and so on. Almost every one is solved this similar way. All right. 11. I actually have an 11 o'clock I got to get to. So,
Okay.
You start school back next week?
On Tuesday.